13.67 is, I don't know, kind of an interesting problem, and it took a lot of thinking to get it right. You got a tray, which I'm going to draw over here, and a ball, which I'm going to draw on top of it. Okay, and then we're going to have a spring below it. So we got a spring below there. Okay, and they say they're going to push it down 15 centimeters below its equilibrium point. Okay, so they're going to push it down. Let's see that right real quick. Okay, so we're going to push it down 15 centimeters below the equilibrium point. This is point A. Excuse me. And that's 15 centimeters. Okay. And the first thing they ask is, how high above A will the tray be when the metal ball leaves the tray? So basically they're going to let it go, and it's going to go down, and then it's going to go back up, and they want to know how high up will it be when the metal ball leaves the tray. Okay. So let's think about it. When it's down at the bottom, when it's down at point A here, okay, the spring force and the spring force is going to be way more. Okay. And when it's at the equilibrium point, like right here, if you think about what the force diagram looks like, it's at literal equilibrium, mg and the spring force will be equal. Okay. And at the point that it leaves the tray up here, at that point, basically the object will be on its own. There will be no spring force. So we have to figure out when that actually happens. Okay. Well, to do that, we have to find out, well, how much is it compressed when it's at that equilibrium point? So we need to find, so for A, first thing we need to do is we need to find x at the equilibrium point. And that's not as hard as we think it is. We're just at the equilibrium point. You can see that those forces are equal right here. So all we have to do is just set those equal. Fs equals mg. And what that means for us is that kx equals mg. Okay, so x is just going to be x is just going to be mg over k. Okay, and that's going to be the mass of both objects. Because remember, there's the tray and there's the ball, which they're crummy enough to give us in two different units. So I'm going to convert them. 1.5 kilograms plus 0.275 kilograms times 9.8 meters per second squared, all divided by that 185 newtons per meter. Okay, and I get an answer of, looks like 0.094 meters. So in other words, like that's how far above the equilibrium point the ball is going to leave. So this point here is actually, if we measure it out, it is from there to there. It's going to be 15 plus, oh, that's weird, let's erase that. Okay, it's going to be 15 plus that 0.094 meters, or 9.4 centimeters, or it's going to be 24.4 centimeters. That's the amount above this point A that it is when it gets to the highest, when it gets to that point where the ball separates. Part B asks how much time elapses between releasing the system at point A and the ball leaving the tray. Sorry. Okay. So it's how much time elapses between releasing the system and the ball leaving the tray. Well, remember, it's leaving way down when the tray is way down here. That's going to be time equals 0. And that's going to be way up here. Time equals something. Okay. And I don't know what that is, but what I'm going to do is I'm going to cheat because it's way easier. I don't want to deal with the phase angle. So I'm going to actually turn this thing on its head. And I'm going to call down at the positive direction. So I'm going to say down equals the positive direction. Because I'm going to have to solve, because I want time, I'm going to have to solve a, oops, sorry, it's I'm going to have to solve x equals a cosine omega t plus phi. Okay. And I'd really like not to have a phi. In fact, I said we should try to avoid it as strenuously as possible. The best way to do it is to say that if we call this, if we call the bottom part here time equals 0, if we can call that the positive direction and call the part above equilibrium, we'll draw a little dotted line for that. So above equilibrium is going to be negative. So this is going to be positive, and this is going to be negative. Okay. So we're going to have to consider that when we think about it. So that means that I can call this 0, which I want to do because it just makes the math a lot easier. Okay. That means that we know that x is 9.4 centimeters above the equilibrium point. Well, that means that because it's above that equilibrium point, we're going to call that negative. So it's going to be negative 9.4 centimeters equals 15 centimeters. I can convert those if I want, but I don't have to. Cosine omega t. Remember, omega is going to be the root of k over m, which in this case is 185 divided by 1.775. Remember, I have to take those and I have to add all those together. Okay. So I put all that down. Okay. I end up dividing both sides. I get negative 0.63 equals the cosine of 10t. I take the inverse cosine, remembering I have to do it in radians, and I get 2.21 equals 10t. My time is going to be 0.221 seconds. That doesn't turn as bad as you think, but again, you have to play that game with the positive and negative. It just makes the math a lot easier. Part C asks, how fast is the ball moving just before it leaves the tray? Well, I'm going to go back and use the equation for velocity. It equals negative a omega sine omega t plus phi. Remember, we made this 0. Okay, so I'm going to put that all together. V equals negative. This time, if I want it to be in meters per second, I have to make everything into the correct units. So my 15 centimeters is going to be 0.15 meters. Okay, my omega is going to be 10. I think it's like 10.2 actually when you actually do it. Radians per second. Sine of 10 radians per second times 0.221 seconds. Okay. You crank through all that, you get negative 1.19 meters per second. Remember, those radians are gonna not be existent. Okay, and it's like, well, I got a negative velocity. There must be something wrong with that. But if we go back to our last picture, we said that negative was going to be up, positive was going to be the downward direction. So this is going to be 1.19 meters per second upward. So it ends up working out in the end.